guys, here is our example video for the calculations for energy, wavelength, and frequency of light. So hopefully by now you've done the reading guide for the first sections in this chapter, chapter 6, and you're ready to tackle some of the problems. So I apologize for this video. It's not the best quality, but I'm doing it at home. So what you've discovered hopefully is that we have an equation that relates our wavelength, which is this Greek letter lambda, to frequency. And they're equal to the speed of light, which is a constant. So it's 3.00 times 10 to the 8th meters per second. So that's how far light will travel in 1 second. It's kind of incredible. And the other equation we have is that energy of a photon of light is equal to what we call Planck's constant times that frequency. So Planck's constant is 6.626 times 10 to the negative 34th joules per second. So that's the amount of energy for every per frequency of the wave. So we're going to take a look at a couple example questions. Our first one says, light from a red sunset has a wavelength of 625 nanometers. What is its frequency? So if we want to solve this, I'm working at a weird angle here. All right, if we want to solve this, we want to solve for the frequency, and so we need that wavelength. Our wavelength is 625 nanometers. The first thing we need to be able to do is convert our 625 nanometers into meters. So we're going to take 625 nanometers, and we're going to convert nanometers into meters. All right, so I had to look this one up. It's been a long time since I've converted nanometers. So there are 10 to the 9th nanometers in 1 meter. So that's our first step, is to get rid of these nanometers and have it in meters to use our equation. So if we calculate this out, we have 625 nanometers divided by 10 to the 9th power. And we get this really tiny number. So I'm going to change it into scientific notation. So 6.25 times 10 to the negative 7th meters. So now we want to plug this into this equation. This is our wavelength, and we're going to solve for that frequency. So we have C equals lambda times a Greek letter nu, and we want to solve for this. So we're going to divide by lambda on both sides, and that cancels. Oops. So we have C over lambda is equal to our frequency. So we need to take our C value, 3.00 times 10 to the 8th meters per second, and we're going to divide it by our wavelength, 6.25 times 10 to the negative 7th meters. And this will equal our frequency. So we just need to calculate. 3 times 10 to the 8th divided by that previous answer. And we get 4.8 times 10 to the 14th. Now, we do have 3 sig figs, so I can do 4.80. We have 3 on both of these, times 10 to the 14th. Oops, times 10 to the 14th. This makes sense, because 8, when we have these exponents, 8 minus negative 7 would basically add those together, so it would be around 10 to the 15th. But with this division, it scoots our decimal over. And our unit left, we have meters canceling out, and then we have this seconds, and they're on the bottom. So our frequency is in 1 over seconds, or it's per second. So we can think of this as, we would read it as 4.80 times 10 to the negative 14th per second. So it's kind of interesting units there. So that's our first example. That would be our frequency of light. So that's how many times that photon of light, or that wave of light, cycles per second. It's a lot. It's a very high frequency wave. All right, we're going to take another example here. So it says an MRI, so a magnetic resonance imaging machine, operates at a frequency of 4 times 10 to the second megahertz. 1 megahertz is equal to 10 to the 6th hertz. So this is megahertz. Okay, is what that is. What is the wavelength? So very similar equation or situation. We want to find our wavelength, and we're given frequency. So we're going to use this equation again. First thing we need to do though is get this into the proper units. We can see up here our frequency units are per second, so we want this to be in per second. So we have 4, sorry again for the video, it's not my best quality. I'm having to hold this thing. So 4 times 10 to the second megahertz. And we want to convert that into 1 over seconds. So 1 megahertz is equal to 10 to the 6th hertz. So we can convert that. So 4 times 10 to the second times 10 to the 6th, and we get 4 times 10 to the 8th. 4.00 times 10 to the 8th. So this is our hertz. Now hertz are equal to the same thing as 1 over seconds. So it's the same unit. They're equal to each other. So we don't have to do a second conversion there. Now we do want to go ahead and solve this question. What is the wavelength? So we're going to use our equation. We want to solve for wavelength, lambda. So if we divide the frequency over, C over frequency will equal lambda. So lambda equals C divided by our frequency. So 3.00 times 10 to the 8th meters per second. That's our C value. Divided by 4.00 times 10 to the 8th, 1 over seconds. So our units, these per seconds, will both cancel, and we're left with meters, which is a wavelength. So we get 3 times 10 to the 8th divided by 4 times 10 to the 8th, and we get 7.5 times 10 to the negative first. So if we wanted to go ahead and put that in normal notation, it'd be 0.75. Now we do want that third significant figure, so we're going to add a 0 because we have 3 sig figs on both, and our units are meters. So that is our wavelength. So it's a pretty long wavelength for this one. All right. So last example, we're going to use our second equation to find energy. So energy is Planck's constant times our frequency, and it says, what is the energy of the photons of light from above? So we want to find from this problem, what is the energy? So energy is equal to Planck's constant times our frequency. Our frequency we have from here, so we're going to use that again. So we have Planck's constant, which is this, so 6.626 times 10 to the negative 34th joules times seconds, and we're going to multiply that by our frequency, which we're going to get from right here, 4.00 times 10 to the 8th per second. So you can see we've got 1 over seconds here, and we've got seconds here. They will cancel, so we're just left with joules, which measure energy. So our energy is 6.626 times 10 to the negative 34th times 4 times 10 to the 8th. So we get 2.6504 times 10 to the negative 25th. We have 3 significant figures, so we're going to do 2.65 times 10 to the negative 25th. Our units are just joules here. So this is energy of of 1 photon of this light. One other question that can come up is finding the energy of a mole of photons. That's a very common question to come after this, especially in multi-part questions. If we wanted to find the energy of a mole of photons, we can multiply this energy by a mole. So it'd be 6.02 times 10 to the 23rd. We multiply them together and find the energy of 1 mole. So I hope this helps out in your calculations and trying that worksheet. If you have questions, send me a message.